Good day. It's been a few weeks for me. I went away to a family trip to Kentucky, and now it's the end of July, and I'm ready to make a couple more videos for you. So today we're going to talk about heat transfer, and including latitude and longitude, specifically the way latitude is related to climate. And also when we talk about heat transfer, how does heat get transferred throughout the atmosphere of the Earth? How does it get transferred from the land to the sea to the air? And so we're going to talk about those kind of things. So we're going to identify the three methods of heat transfer. So this will be three vocabulary words. We're going to practice methods of identifying global locations, and we're going to relate this to the research in the green home location. So to start off with, I have a quick video to show you related to heat transfer. It'll be where is it? That one. I don't know if any of you know what the jitterbug is. Jitterbug is a dance that my parents danced. I didn't really dance it myself.
Another cup given away to the winner of the Jitterbug contest.
Now, some of you might be wondering, how is this related to heat transfer? Well, when you talk about heat transfer, we're talking about what's happening to the energy levels at the molecular level, at the atoms.
What's on here tonight? What? The Jitterbug contest. Did I hear him say Jitterbug? Yeah. That's me.
So when they're dancing around, we're supposed to think of them as being atoms and molecules, moving around, and jumping around. And I could never dance like this myself. Maybe some of you can, but this took a lot of energy, a lot of strength. All right. So anyway, atoms move around a lot. Not that far, not that much different from the way those people were moving around on the dance floor. And the more energy they have, the faster they go. And the more energy they have, the hotter it is. And if one of those really fast-moving molecules touches you, if it's hot enough, the energy will get transferred onto your skin. You'll feel pain, you'll feel a burn. And that's just one way that heat energy can get transferred to you, is by touch. So let's go back. So when we talk about that, first of all, many of you maybe you don't know what the word jitter means. So if that dance is the jitterbug, what do you think jitter means? What would be a synonym for jitter? Go ahead and write it down in your capture sheet. There is no one right answer, so when you come into class, I'll be asking you what you wrote down for there. Now, what did I say causes atoms to jitter, or to wiggle around, or move around? You know, we said that energy, specifically heat energy, causes them to move around, and the effect of all that heat energy is movement, or vibrating atoms. Now, when we talk about heat transfer, that energy can get transferred in a bunch of different ways. For example, we can transfer heat through touch. And the reason I put that in the definition box is because there's a fancier word for that, and it's conduction. And then there's just heat mixing around and rising. Hot things rise, cool things sink. I'm just going to write heat, rising, cool, sinking, and we call that convection. I would be really curious if someone could come in to class next time and have some sort of clever way of telling the difference between conduction and convection. I'd be happy to give a piece of candy or something for that. And then the last one is when heat just, well, for example, when we talk about the energy of the sun going across space and getting to the earth, it goes across a vacuum. That energy traveling through space, we call that, I have a name for that. Energy travels through space, we call that radiation. All right, so an example of conduction. You know, it's heat transfer by touch. So it's sort of a, you know, if you have a hot pan, when it cooks the food, that's touching it, that's on top of it. Convection. You know, if we stick with the food, when we have a pot of water, H2O, and we heat the bottom, and the water that's at the bottom rises because it becomes less dense, and then it sinks as it cools off, and that it naturally mixes together so that the entire pot, that heat ends up getting spread through the entire pot, making it hotter and hotter. That's an example of convection. And then I already mentioned the sun radiating energy across space until it gets to the earth. Hopefully everyone understands that's not a scale drawing. If that was as big as the earth was, I'd have to make the sun as big as the board, the entire board, and then the distance, I wouldn't even have room for the distance. We'll do scale models of the sun and earth when we do our astronomy unit. Okay, so one of the things you brought home was this article, Jittering Atoms Chase the Cold. What I'd like you to do is hit pause on the video and just go ahead and read through the article, marking parts of the article that you think are confusing with IDK. If you read something and say, oh yeah, I know this, right, put a little smiley face by it. If you're surprised by some information, you can put a exclamation point. And what I'm really going to be looking for is I want you to identify all the definitions and all the examples that are in the reading. So go ahead, hit pause, and take a moment and read all that. Okay, so I just gave you some words and examples. We're going to put it down again. Now, one of the things I did mention, though, is as long as the temperature is above a certain temperature, and there's a special temperature in which, because we said that heat causes the molecules to jitter around, to vibrate around. And so the hotter it is, the faster those molecules are going to move around. In fact, when we talk about solids, liquids, and gases, we talk about solids, you know, the molecules aren't moving very fast, and so they're sort of stuck in place, and it's a nice solid. And then when you add more energy and the molecules bounce around, eventually they break free of that solid and they start to flow around. That's called a liquid. And then when we heat that liquid enough, so there's enough energy so the molecules break free of being a liquid, that's when the liquid is boiling and it turns into a gas, and then it becomes a gas. And then if we heat the gas even more, and it has so much energy that the molecules are vibrating so much that the electron shell around the nucleus is released, we call that a plasma. And that's actually the state of matter that's in the sun. Some of you didn't know there was a fourth state of matter. So we have solid, liquid, gas, and plasma. And it all has to do with how much energy the molecules have. So what happens when it gets colder? That means that the molecules vibrate less and less. And eventually you get to a temperature that's so cold that the molecules are absolutely still. And you can't get any colder than that because molecules can't vibrate slower than 0. And we call that temperature absolute 0. And the atoms, as long as it's above absolute 0, the molecules are dancing around. And then, as the temperature goes up, the hotter an object, the faster the atoms vibrate. I think I actually have all of this filled out on the next slide. Let me just double check. Yeah, I wrote, before I wrote absolute 0, and I said the warmer an object, hotter, warmer. And then we have the words, conduction, radiation, convection. A nice definition for conduction is heat energy transferred by touch. Remember I mentioned touch earlier, when atoms are actually hitting each other. A foot standing on the hot sand is a nice example of that. Radiation, heat energy transferred through electromagnetic waves through air, space, but not touching. The sun sending its energy to the earth. And then heat energy, convection, heat energy transferred in a fluid. Now fluid is defined as anything that flows, so that could be a gas or a liquid is a fluid. And it's transferred into fluid by the movement of the fluid. So if you have a heater and you have air above that heater, when that hot air rises and the cooler air comes and sinks down and gets heated, and eventually the air in the room gets hotter and hotter and hotter. So when it says cold air, I'm really not talking about cold air. I'm talking about air that's cooler than this air. So this air rises, the hot air rises, and whatever air that's cooler than that will sink. And then as the room temperature gets hotter and hotter, the air that's sinking is actually a little bit warmer than the air that sank before, but it's still cool compared to the hot air that's rising here. So, let's watch another little example of actually I have it right. There. All right, let's play this.
There are 3 ways to transfer thermal energy. Let's look at conduction first. In conduction, energy is transferred by particles that are in direct contact with each other. The heat from the flame causes the tiny particles that make up the pan to vibrate faster. The pan particles bump against the butter particles, making them vibrate faster as well. As more and more of the vibrating particles come into contact with each other, the butter gains thermal energy and begins to melt. It has been heated by conduction. The second method of thermal transfer involves fluids, materials that flow, such as air and water. This method is called convection. Energy is transferred when matter flows from one place to another. Heating the air in the balloon creates warm air flows that are forced upward by cooler air flows that fall. The third method of thermal energy transfer is radiation. An example of radiation is the energy we receive from the sun. This energy is carried by electromagnetic waves that travel at the speed of light. When the sun's radiation reaches Earth, some is reflected back into space by the atmosphere, and some is reflected by Earth itself. The remaining radiation that reaches Earth is absorbed. It becomes thermal energy. You experience thermal energy when you touch a parked car that's been warmed by the sun.
Okay, so we talked a little bit about that idea of the energy budget last class. So energy from the sun, some of it bounces back into space, but it's still radiation coming from the sun, and that radiation is in the form of light, infrared, ultraviolet, and then of course some of the other ones like gamma rays, radio waves, all kinds of electromagnetic radiation. Infrared is the kind of radiation, like if you go to a fast food restaurant and they've prepared the food and it's underneath the heat lamps, that's infrared radiation radiating heat down to help keep the food warm until you buy it. I used to work at McDonald's when I was 16. I worked behind the grill, and I'd make the food. And if it had been sitting there for more than 15 minutes, we were supposed to throw it away. Okay, so we got 3 types of heat transfers: convection, conduction, radiation. Say that 3 times to yourself, a few times, so that you remember those words. We see that again on quizzes and tests. Convection, conduction, radiation, and then try to remember examples and definitions. So one of the things that affects how much heat energy gets to the Earth is your position on the Earth, specifically latitude. So so some of you, we need to review a little bit about how to read a map and what latitude and longitude are. Again, I have another video clip.
We've already seen that the most important map grid is the geographic grid, the one used on globes, which is made up of latitudinal and longitudinal lines expressed as meridians and parallels. Using this grid system, every place on the Earth can be pinpointed exactly. In fact, every place on the planet has a global address. Using the geographic grid, let's see how this address is expressed in degrees of latitude and longitude. For example, Phoenix, Arizona is 33.5 degrees north latitude and 112 degrees west longitude. Kansas City, Missouri is 39 degrees north latitude and 95 degrees west longitude. South of the equator, the degrees of latitude are south, so that Buenos Aires in South America is 35 degrees south latitude and 58 degrees west longitude. On the other side of the prime meridian in Europe, a city like Vienna, Austria, is 48 degrees north latitude and 16 degrees east longitude.
Okay, so the latitude and longitude, we have lines like here. We call this line, we know, hopefully everyone knows this is the equator. Let's see. Oop, I don't want to do that. So we have the equator, and then we can have the what we call the prime meridian. So if you were graphing in math class, you'd call this the 0 line for the y-axis, and we call this the 0 line for the x-axis. This is 0 for x, and this is 0 for y, and then when you go up, your y increases. When you go down, your y becomes negative, x becomes negative, x becomes positive. In this, though, we instead of becoming positive and negative, when you go above the 0 line, that's north. And eventually, when you get up here, that's 90 degrees north, and that's 90 degrees south. So for a total of, half of a circle, that's 180 degrees, 90 degrees one way, 90 the other way. And then when you go this way, this is supposed to, if you think of a globe that has been cut open and spread out, this edge of the globe touches this end of the globe. So this is 180 degrees towards the west, and this is 180 degrees towards the east. And so if I said I was at 30 degrees north and this is about 15 degrees north. 30 actually, where Rockville is right around 34 degrees north. And then now here's a question: when you're graphing, your Your horizontal lines are straight, but your vertical lines are also straight when you graph on a graphing paper. Why are the lines curved on this? Anyone have any thoughts? Think about that for a second. When you think about the shape of the Earth, and we're taking a globe, which is a sphere shape, and then trying to put it on a flat surface, we end up with nice curved lines. Okay, so when you look at a map, you have numbers on there, you're going from 0 up to 90, 0 down to 90, and so in your capture sheet, I'm hoping that you can find the location of a few different places on the map, and so go ahead and do that work and bring it in, and enjoy the rest of your day.